Hi, this is video lecture of section 9.2, second part, part 2. Okay? So in the first part, we studied what is a vector, two-dimensional and three-dimensional, geometrical representation, and component representation. And also learned how to do constant multiplication or scalar multiplication of vector and the addition of two vectors, geometrically and component-wise, both. Okay, now second part start with unit vector. So if the magnitude vector equals 1, then V is called a unit vector. Unit vector is nothing but a vector of this size 1, vector of size 1. Okay? It doesn't matter which direction it is coming from. Now, in two-dimensional case, the most important unit vector will be 1, 0, I hat. 0, 1 point over here, and J hat. So I hat, well, because it is so awkward, we actually take off dot. And hat a lot of times means unit vector, alright? So it's 1, 0. So I hat is a unit vector in the positive x direction. J hat is a unit vector in the positive y direction. And of course, in three-dimensional case, this is x, y, and z. Then we can think about I hat, j hat, k hat, same way. I hat equals 1, 0, 0. J hat equals 0, 1, 0. K hat equals 0, 0, 1. These are standard unit vectors. Okay? Standard unit vectors. Now, these standard unit vectors can be used to write component form of a vector slightly differently, like this. Let's say your vector V as component A1, A2, A3. Okay. You can write this one as A1, 0, 0 vector plus 0, A2, 0 and 0, 0, A3. You can do that. Component-wise addition will give you A1 for x component and so on. And then this one is actually same as scalar multiple A1 times 1, 0, 0. A2 times 0, 1, 0. A3 times 0, 0, 1. Okay? And then, what is 1, 0, 0? That's precisely I hat, right? I hat, J hat, K hat. So, in order to describe component form of a vector V, you can use angular bracket A1, A2, A3, or A1I, A2J, A3K. It's the same thing, actually. In fact, a lot of engineering textbooks tend to use this way, rather than writing this way. There are some advantages of using this one, especially when you try to derive a formula of the vector product. But personally, I believe this is more compact. And also, when you study math a bit more advanced ones, we no longer consider V as just some kind of error, physical. It's just ordered triple. of real numbers for three-dimensional vector. Okay? So then you can consider any dimension of vectors easily, algebraically easily defined. So anyway, either way is fine, but I personally prefer this notation. Okay? All right. Then, okay, you can think about this graphically as a vector addition. A1I, if you go A1I, that means this point is A100, right? This is A2J, means you're going A2 along the y direction. Let's say A3K as a vector. That means this length is A1, A2, A3. And then vector addition, back to back to back, and this will be your vector V. That is A1I, A2J, A3K. Just vector addition. But then, coordinate-wise, this point P is actually A1, A2, A3. So in component form, original component form, this is A2, A3, right? So they are same thing. All right. So example 5. Example 5. If vector A equals 2I minus j plus 3k, and vector B equals 3I minus 2k, express three A minus 2B in terms of I hat, j hat, k hat. Okay, let's do that. 3A vector minus 2B vector. Oh, I forgot to do, before I do this one, I forgot to do a very important thing. Okay, so actually our second part of the lecture should have started with this. Properties of vectors, properties of vectors of any dimension. Okay? Here, first, vector A plus B equals B plus A. In any case, 2. A plus B A plus B plus C. Okay? 3. So first vector is about commutative property of vector addition, associative property of vector addition, existence of identity in vector addition, and existence of additive inverse. Obviously here, for all A and B, for all vector A and B, for all vector ABC, for all vector A, for all vector A. All right, just right. And then you have a kind of distributive property of A, alpha B. All right. Another kind of distributive property times A should be A. These are 8 most important properties of vectors. In fact, these 8 forms a definition of vector space. Okay? This is 8 axioms which defines something as a vector space, collection of vectors, as we know. All right? Okay. And here, let's go back to this. So, 3 times 2I hat j hat plus 3k hat minus 2 times b 3I hat minus 2k. So, using this property, this distributive property, this is distributive. Okay, 3 times this. And then this is 3 times 2i. 3 times 2i is equal to 3 times 3 times 2 times I. So 6i. So we're using this property and this property together. 3 times -1, so -3j. 3 times 3, 9k. Minus 6i plus 4k. And then combining like terms, or these two cancel. Minus 3j, 9, 13k. Alright? So you get this. Now, or you can write this one as in component form. What was the component form of this? Just angular repeat 2, -1, 3. Alright? And then this one. Minus 2b, 3, 0, -2, isn't it? Alright? So, here, if you multiply this one by 3, then 6 minus 3, 9, 6, 0 minus 4, subtract 0, minus 3, 13. Okay? In the end, you're going to get the same thing. Alright. And then we want to learn about a unit vector in the direction of something else. It's not a vector. Okay. Suppose that let's say vector A. If magnitude vector A equals 4, then the unit vector in the direction of A. So, a unit vector which is the same direction of A. How do you write it? So this is length 4. Length 4. Alright, length 4. Same direction of A, but length 1 should be 1/4 size, isn't it? Let's say I'm going to use U. So 1/4 of A, same direction. So in that case, you should be just 1/4 times vector A. Or you can write it as 1/magnitude vector A times A, isn't it? Right? So in general, if vector A is not zero vector, then the unit vector U in the direction of A is given by 1/magnitude of A times sometimes they just write it this way. It's not that we divide vector A by some scalar number, some real number. Original meaning of this notation is 1 over magnitude of A as a constant multiple, scalar multiple of vector A. Alright? So, example 6. Find the unit vector. Find the unit vector u in the direction of A, which is 2, negative 2, 1. Okay. First of all, magnitude of, what is magnitude of A? That is square root of 2 squared plus negative 2 squared and 1 squared. Square root of 9. It is 3. Right? So, unit vector in the direction of A is 1 over magnitude of A times A. So, that means 1 over 3 times vector 2, negative 2, 1. So it's going to be 2/3, negative 2/3, and 1/3. Okay? That would be the unit vector in the direction of okay. What if I change the problem? Find the vector v. Let's say, if I change, let's say, a variant from 6 prime, let's say, slightly different. Find the vector v such that, such that your magnitude v is 5 and v is in the same direction. V has the same direction of A. But v is not unit vector, is it magnitude 5? So v and A and u, all of them have the same direction, right? In that case, your v will be just what? Magnitude 5 is 5 times the size 1, right? It should be 5 times u. Alright? So it's going to be just 5 over 3. Alright? Or 10 over 3 minus 10 over 3. See? This is the key. 5 over original length of A, 3. Okay? Original magnitude of A is 3. Our magnitude of the new vector, 5. And you're going to get the same direction vector with desired magnitude. Okay? So you could think about slightly different things here. Alright, our last example. Our last example is example 7. Let's say you have a ceiling. There are 2 strings attached to some mass. Let's say this is 100 pounds. Now this one has 45, this string has making 45 degrees, 60 degrees. Then I want to know the tension on the first string. What's the tensions on each T1 and T2. So I want to know the tension. Tension is the force applied by a string. Okay? I want to know these two tensions. Okay? In this situation, hanging weight. All right? So 100 pound weight is hangs from two wires. Hangs from two wire, as in this figure. Okay? Find the tensions. Find the tensions. Tensions is just the force. Okay? Applied bias wire for string. Applied in the wire. Same thing. T1 and T2 in both wires. And their magnitude. Okay? So this will be the last example. Before we do this, let me check recording. Okay. Okay, let's think about now. If there's no weight and only tensions, then this point will be just accelerating upwards. These two tangents combine to balance with gravitational pull on that weight, right? And these three forces should be canceling each other. That means sum of these three forces must be 0. Because this is not moving. In order to, in order for an object not moving, well, actually, no acceleration means that no net force is applied. So that means the sum of these two vectors, let's say, actually, what am I doing? This is longer. Sorry about that. This T1 T2 okay, T2 must be short. So then the sum of these two vectors, okay, this is T1 plus T2 force must be exactly opposite force of this weight. It's gravitational. Okay? 100 pounds. Okay? So if I draw x-axis like this, this is it should be vertical force. So your Fg, gravitational pull, will be 0 minus 100 because it's going down, right? So in order for this weight to stay put, therefore, sum of these two forces must be 0 positive 100, so that the net resultant, the sum of these three forces add up to be 0 force, right? So this is the clue. T1 plus T2 must be 0, 100. Okay? So this is 60 degree, that means this is 60 degree, and this is 45 degree, all right? This is 60 degree, 45 degree, T1, 45 degree. Now let's analyze this. So let's find the components formula. So this magnitude is T1, let's say magnitude, T2 magnitude. Then your x component is negative of this length, right? This is T, this length times cosine 60 degree, which means 1/2, right? So your T1 as a force vector minus T1 magnitude cosine of 60 degree. And T1 magnitude, this length y component is sine 60 degree. So it is just magnitude minus this one over 2, square root of 3 over 2, T1. Alright? Likewise, T2, look at this. 45, cosine 45, T2 magnitude times cosine 45 degree, and T2 magnitude, y component, sine 45 degree, which is just square root of 2 over 2 T2, square root of 2 over 2 T2. Okay? So, what is it? T1 plus T2, component-wise, you have to add these. Minus magnitude T1 over 2 plus square root of 2 over 2 T2 magnitude, alright? And then y component addition will give you square root of 3 over 2 T1 magnitude, square root of 2 over 2 T2 magnitude. We know that this has to be 0, 100 force, right? That's why you get this, all right? So we have to, so that means minus T1 magnitude over 2 plus square root of 2 over 2 equals 0, square root of 3 over 2 T1 Hey, this is a system of linear equation in two variables, magnitude of T1 and magnitude of T2. So from here, 2 to cancel. So T1 magnitude equals square root of 2 T2 magnitude. Alright? And then combine it here. So square root of 3 over 2, square root of 2 T2, 100. Multiply both sides by 2. Square root of 6 T2, 2 T2 equals 200. Okay? So square root of 6 plus 6 square root of 2 times magnitude of T2. Alright? Therefore, magnitude of T2 equals 200 over square root of 6 plus square root of 2. If you want exact value, you can stop there. Or you want to rationalize and see where it goes. So This is 6 minus 2, 4. Square root of 6 minus square root of 2. 200. So this is 50 times square root of 6 minus square root of 2. Anyway, in this case, decimal value would be better. 51.8 pounds, horsepower. Well, what about magnitude of T1? Well, which is square root of 2 times magnitude of 2. Well, distribute this. Square root of 12 is 2 square root of 3, right? If you distribute minus 2. 100 times square root of 3 minus 1. Anyway, that will be about 73.2 pounds. Okay? So, you will know how much of tension will be applied to the first wire and second wire. So, you can choose the right spec wire thickness to withstand the expected tension. Alright? So, this is the end of section 9.2. This is a review of vector you learned in pre-calculus. In pre-calculus you only learn two-dimensional. Maybe in some cases also three-dimensional. Mostly two-dimensional. And we also introduced three-dimensional and vectors and component-wise addition, geometric representation. And so this is a review, mostly review of what you learned in pre-calculus. And next section, 9.3, you will learn dot product. Also you learned it, math analysis in high school or pre-calculus. And 9.4, cross product. A lot of time, high school do not teach that one. And also in our pre-calculus school, we don't teach cross product. So 9.4 will be probably new materials to many of you. Okay? All right. This is the end of section 9.2. Thank you.